started. Today we're very fortunate to have Sam to tell us about Adaptivity.
All right, thanks so much. Thank you for coming, everyone. Yeah, so today I'm going to talk about the theory and practice of adaptive filters. So a little bit more details of that. So the plan for today is the talk is going to span a handful of papers. That's why I didn't have co-authors on the first slide. We're going to kind of be moving forward through time, but also we're going to start with kind of what we're trying to do, a little bit of motivation, a little bit of background, and I'm going to talk about theoretical guarantees. And in particular, today I'm going to be talking about data structures. In the first part of the talk, I'm going to be talking about strategies for how to put these data structures together, but a little bit less about what bits go where and that level of detail. In the second part of the talk, I'll go into a little bit more about detail. Exactly how we build these data structures up and exactly what they look like. So when I say practice, I don't really mean practice. I mean practice from kind of a theoretical point of view of what exactly we're doing. All right. So when I say filters, I'm talking about a succinct data structure that's often used to speed up database queries. So I mean filter in the sense of Bloom filter. I know this is kind of an overloaded term in theory in general. So a Bloom filter is kind of a classic example. So to begin, I want to talk a little bit about how a succinct data structure can help make database queries faster. So if we want to store a bunch of stuff in a database, it takes a lot of time to access my database because the database is very big. It's very far away from me. And in a database, a lot of really common workloads have a lot of unnecessary queries, a lot of queries that access keys that aren't even in the database. And I'm still accessing this big database to find their corresponding value. So in particular, I'm going to say today that S is the set of keys stored in my database. I'm going to maintain that notation throughout the talk. So the classic example, this is actually the original Bloom filter motivation, believe it or not, was it's 1971 and you're Burton Bloom and you want to create a dictionary of unusually hyphenated words for a spell checker. Most words have normal hyphenation rules, but you need to keep querying this database just in case you come across a word that has an unusual rule for hyphenation. A little bit more realistic in a modern sense is checking if a key exists before an insert. So often when we insert into a database, I don't want duplicate keys. So I check to make sure it doesn't exist. The vast majority of the time, the answer is going to be no, it doesn't exist, but I still have to do this wasteful query. Bloom filters are often used on modern computers to check for malicious URLs. Every time you access a URL, your computer checks if it's on in a list of known malicious URLs. Most URLs aren't malicious, but we have to check it out. In general, any kind of table with a lot of empty entries is going to be a good use case for a filter. So a classic filter usage is a succinct data structure that will allow us to filter out negative queries. That's why it's called a filter. This isn't the only way you're going to use a filter, but it's one of the most common ways. So before I give a quick example of this, the key properties of a filter, we want them to be really small. We want them to have no false negatives. It's really important for this use case. So a query, if I query an item that actually is in my storage set, I always want the correct answer. I always want my filter to say that that item is in this set. And a filter needs to have a bounded false positive rate. So if I query something that's not in this set, I'll get an incorrect answer saying that it is, with probability at most epsilon, where we get to choose the epsilon when we set up our data structure. So why am I talking about databases? It's going to look something like this. So we're going to have a filter that's so small it can fit in local memory. It's really cheap to access relative to my database. When a query comes in, I can, for a really cheap cost, ask my filter if this query is in my set of keys. So there's a fast in-memory query. If my filter says, yes, this is actually in your set, then I access the database. So if my query actually is in my set, this is something I wanted to do, right? I want to actually access my database and get the corresponding value for this key. If I made a mistake, if this is a false positive, I'm still going to do an unnecessary memory access. So I'll waste time just like I would have without a filter. But the benefit of a filter is that when it responds that Q is not an S, I don't need to access the database at all because I'm guaranteed that this key is not in my database. So a filter can achieve false positive rate epsilon with n log base 2 of 1 over epsilon plus order n bits of local memory. So with a small amount of local memory that only depends on your cost per key, only depends on epsilon. It doesn't depend on how big those keys were in the first place. I can filter out most database accesses keys, not S. So often we're going to have this be something like 1 byte. So epsilon is going to be 1 over 128. So with like 1 byte per key, give or take, I can filter out 99% of my unnecessary database queries. This is why filters are so useful. All logs are base 2 today. Yeah, so it greatly reduces the number of remote accesses, thereby reducing the time it takes for my database. So here's the formal notion of a filter. We want to store a compact representation of a set S. We want to answer membership queries, is Q and S. We're going to have lossy compression, so we can make mistakes, but a specific kind of lossy compression. The answer Q, not in S, is always correct. In other words, if I query an item in S, I always have to get the correct answer. A false positive, where we answer Q in S, whereas in fact, Q is not in S, must happen with probability at most epsilon. And today we want space n log base 2 of 1 over epsilon plus order n bits. Yeah.
Sorry, what's that again?
N is the size of S. Thank you. I think I didn't say that. Yeah, n is the size of S. So let me talk a little bit about how filters work. And again, this is going to be a strategy and not super high level of detail. So a lot of you have probably already seen Bloom filters. They work something like this. You hash each item multiple times and you maintain a bit vector of zeros and ones. We're not going to use this today. This gives you slightly worse space than what I want. You get like 1.44 n log 1 over epsilon bits. Instead, we're going to use a more recent kind of filter called a single hash. So for a single hash filter, we're going to choose a random hash function. Our hash function, so U is the universe of possible items that encompasses both all of our queries and the set of items we want to store. And we're going to hash it down to one of n over epsilon values. Let's just assume n over epsilon is an integer. All we're going to do is we're going to store the hash of every item in my set. That is my filter. So my filter is I take my n items, I hash all of them, and I store those n hashes. Each has one of n over epsilon different values. To query, we look up in the filter and we see if this hash is stored, if the hash of the query is stored. So we hash the query, and then we see if this hash is something that's actually stored. If so, we say that the query is in our set. All right, right away, we get no false negatives. If I query for something, if it was in the set, we must have stored the hash. So we always say that the query is in the set. And we also immediately get false positive probability epsilon. So the way this works, let's look at a single item in our set. The probability that Q and that single item have the same hash is epsilon over n, because we're hashing uniformly randomly to one of n over epsilon different values. So we're going to just assume fully random H today for simplicity. You can get rid of this assumption if you want using known hash functions. So we take the union bound over all n items. N times epsilon over n gives us a probability epsilon that a given query collides with any item in our set. So just by taking all of our items and just hashing them down to this set of size n over epsilon, we immediately get all of our query guarantees that we want. But we want a little bit more than this. We want space. So let's talk a little bit about space. So my goal is I want to store n hashes, each from 0 to n over epsilon minus 1. The entropy of this set I'm trying to store is log base 2 of n over epsilon choose n at most. And this turns out to be n log 1 over epsilon plus order n. And that second term actually is intrinsic to this n over epsilon choose n. So when I said that this is how much space we want, it's basically right away from this entropy bound. So I want to store these n hashes in space close to this entropy bound while still allowing fast lookups. So you can do this. You can just throw all of this in a dynamic dictionary. This is the part I'm sort of going to gloss over. You can use a classic dynamic dictionary if you want. You'll get very close to this bound. For filters, you can actually do a little bit better, partially because we're going to be storing the number of elements you store is very close to the size of the universe of elements we're storing, n over epsilon versus n. And then also all of these things we're storing is random because we're storing hash values. So keeping these two things in mind, you can actually do better than classic dictionaries. So the paper I'm about to talk about actually did out some of this back-end stuff. You can get within little over 1 of this n log 1 over epsilon term plus order n space.
So like classic dictionary means the binary search tree or something like this?
You could do a binary search tree, but that's not succinct. I'm thinking something like backyard hashing, where you get very close. Basically, the space bound is close to the entropy term. There's like trie-based data structures that actually get very close to this. Recently you can actually do everything perfectly up to constants. So you can get log base 2 of n over epsilon choose n plus little o of n space, and all operations are constant time. Yeah.
Just to clarify, when you say O1 operations, that's like O1 underlying operations per like query.
Oh, sorry. No, this is time per operation. It means I can insert in constant time, I can delete in constant time, and I can query, is this hash stored in my dictionary, all in constant time.
Okay. And do you have to know how many elements you want to support ahead of time, or is it dynamic?
You have to know how many elements you want to support ahead of time, or you cannot achieve these bounds. There's a log u lower bound. And a lot of interesting papers along those lines, actually. Log u per item, I guess I should say, like n log u. All right, so what are we going to do with this today? And I'm going to sort of talk about lower bounds, and I'm talking about what I want to do. So I want to improve Bloom filter performance. I want to do better than this n log 1 over epsilon plus order n space, no false negatives, false positive probability epsilon. What can I improve by this? What can I improve about this? Like, it'd be really nice, for example, if I could improve the space. I think it's really, it's both a really sort of clean proof, and I think it's sort of educational how it actually works. Can you do better than n log 1 over epsilon space? So the answer is no. There's this classic lower bound from 1978. So here's how this lower bound works. This is just sort of a one-slide proof. So if I want false positive probability epsilon, I want my memory representations on average. I'm not saying on average on this slide, but on average. I want each memory representation to store at most an epsilon fraction of my items. Right? I want only epsilon u items to be items where the filter says yes. This must be a superset of the n items I'm actually storing in my filter for this memory. So if I'm using a given memory representation to store a given set of size n, the things I say yes to must encompass the items actually in my set. That's required by no false negatives. So these sort of correspond to filter guarantees. False positive probability epsilon on the first bullet point, no false negatives on the second bullet. So a given memory representation can only be used for epsilon u choose n sets. So those are the only sets of size n that are a subset of my false positives for this memory representation. I have to eventually store all u choose n possible sets. I want to be able to store every set. So I need u choose n divided by epsilon u choose n memory representations.
With u again?
U is the size of our universe. And the u's all cancel in terms of the final thing. Yeah, exactly. So if u is the size of my universe, then all sets is of my possible elements I could have in my filter. I need to choose the n things that actually are in my filter. So my space is at least log base 2 of this term. Any sort of normal things you can do to handle binomials will get you that this is very close to n log base 2 of 1 over epsilon space. So I can't do better than this in terms of space. In particular, so I can't reduce the number of false positives without increasing the space, which is too bad. What I want to talk about today is, can we choose which elements are false positives? So these might both be, this is sort of an abstract representation. This is my universe of items, and the dots represent things that my filter says yes to. These are both legal representations in terms of this lower bound, because they both have an epsilon fraction of the universe saying yes. But both of these work, and some might be better for me than some others. Maybe I can change which elements are false positives. But we have to be sure. So let's say that the red elements are the elements in my set S. As I'm changing my memory representation, I need to make sure that the elements in my set stay as elements that I say yes to. So as I'm moving around false positives, I need to be very careful to not introduce false negatives. So that leads me to this concept of adaptivity. So this is sort of a fun motivation, and this is from an older paper. So the Bloomier filter paper, which was from 2004, kind of a follow-up to Bloom filters. What the Bloomier filter paper actually did is it's a kind of Bloom filter that stores a function on each of the elements in your set. But their motivation was really interesting and actually a lot of fun. So this paper was written in the early 2000s. In the early 2000s, there was this no-fly list. So there are all of these names on the no-fly list of people that weren't allowed to fly. So ticket agents at Los Angeles Airport noticed that there are some problems with this no-fly list. In particular, there is this name David Nelson on the no-fly list. Unfortunately, David Nelson is a really common name. So day after day, they had David Nelson coming up to the ticket counter. David Nelson's not supposed to be on the no-fly list, but over and over, they had to manually process this person through. There's even a quote from a ticket agent saying, "Oh boy, here's another David Nelson." So the lesson here is that not all false positives are the same. Not all false positives are the same cost for us. The way the Bloomier filter paper handled it is they said, oh, if we can store a function on these elements, then I'll have some elements that are on a whitelist, some elements that are saying, I'm definitely sure this is not a false positive. So that kind of addresses this problem. I could do something like on my list, I could give a list of really common, let's say, names. It has to be at most order n. I could give like the n most common names, and I can guarantee that those are never false positives. So that was their motivation, and that's how they addressed this problem, by saying that some things are never allowed to become false positives. But I think that's not really what you want to do. I think what you really want to do is have the ability to fix false positives when a false positive comes. So that if David Nelson comes to the counter, I'm saying this is a problem, you're not actually supposed to be on the no-fly list, I'm able to fix it. So as we sort of looked at in these lower bound diagrams, we want to move things around so that if a query was a false positive, it's not a false positive anymore. So in terms of like the lower bound we saw on a false positive Q, we want to change to another memory representation so that we're still correct for all items actually in our set, but is also correct on this item Q. It answers Q, not an S, for some reasonable probability. In terms of formalism, I think the strongest notion of adaptivity is adversarial. So a computationally unbounded adversary cannot create a false positive with probability more than epsilon. So this encompasses, oh, if I see a false positive once, I don't want it to be a false positive again. An adversary would be able to catch on to that really quick, right? But it also, I want a notion of adaptivity that works against any kind of strategy to make some false positives more common than others. So I'm going to go into more detail about this. So here's a more formal definition of adaptivity and an adversary in a sense. So I'm going to have an adversary generate a sequence of n queries. When generating query I, the adversary knows the result of queries 1 through I minus 1. So it knows if each one of these queries was a false positive. The adversary also knows our data structure and how it works, but the adversary doesn't have access to our randomness. In particular, the adversary doesn't know our hash function. The adversary has access to everything else, all previous queries and the results and how our data structure works. We want a sustained false positive. We want a false, so a sustained false positive rate is the false positive rate of a filter against such an adversary. A filter is adaptive if it can be tuned to achieve any sustained false positive rate epsilon. So I want, as queries come in, even if they're generated by an adversary that's trying to drive our false positive rate as high as possible, I still want to achieve false positive probability epsilon. And when I say computationally unbounded adversary, really what I mean is that I want this guarantee to be information theoretic. So the goal is I want to achieve the sustained false positive rate of epsilon without any extra space. So I still want n log 1 over epsilon plus order n bits. The only sacrifice is we're going to get a slightly worse constant in this order. So in other words, I want that every query has false positive probability at most epsilon, regardless of the result of all previous queries. So I ask a query, it's a false positive. I ask it again, it's not a false positive. And even something, if I'm alternating between two queries, I still want false positive epsilon every time I ask a new query, no matter what. All right, so a little bit more of motivation why I care about adversary. Fixing common false positives. right? A lot of common workloads are going to have some false positives more than others. If I can fix those, I'm just going to get better performance. And a little bit later in the talk, when we're sort of in that second part, I'll give some examples of how you can actually get much better performance in practical days. But there's also some other reasons why you might want this. There's security implications. It's not usually a good idea to allow your users to slow down your database, just sort of on principle. It's also good for consistent performance. So a normal filter, just linearity of expectation, if I have X queries, I'm going to have X epsilon database accesses and expectation. Right? In particular, if all X accesses are to the same element, I have probability epsilon of X accesses and probability 1 minus epsilon of 0. Really, we'd like concentration bounds, which is what the adaptive filter achieves. The adaptive filter has X epsilon accesses with high probability as long as X gets sufficiently large. The more queries I ask, the closer I'm going to get to an epsilon fraction of my queries, leading to a disk access. So you can just, one way to view this is just sort of as concentration bounds for filters. All right, so there's one assumption to the model before I delve into how adaptivity works. We're going to assume that we can access S, the original set of items, to help fix a false positive. And the reason why I'm okay with that is that accessing S is free anyway. That's why I did all of these diagrams. We accessed it due to the false positive. And the idea here is without this assumption, we risk removing the original element that was causing this false positive. So in particular, if I have a query, my filter says, yes, it's a false positive. I was already accessing my database to find out whether it's a false positive or not. As I'm accessing my database, I might as well go and get some advice if that advice is useful for me. Ideally, this should be cheap. Like I don't want to transmit the entire set S. That would be really wasteful. But I'm doing this remote access anyway, so I can get some more information about this set I'm storing if it helps me fix the query. The amount of time I sort of cross this barrier remains exactly the same. In particular, just to be clear, I'm not going to get advice if Q is not an S. All right, so I have some advice, and I want to fix false positives. How can I fix a false positive? We're storing the hashes of all of these elements. That's how my filter works under the hood. One thing you might be thinking of is maybe we can change the hash of the element causing this false positive. We're going to come back to that. It does, well, we'll see. It does kind of work, but it's a little bit difficult to get it to work out of the box. Sort of the problem is we need to make sure that however I'm changing the hash of my stored element, I need to keep track of how I'm changing things for my queries so I don't have any false negatives. What we're going to do instead is add bits to our hash. So what I mean by that is when I hashed all of our elements to this universe of size n over epsilon, I can represent each of these hash values using log n plus log 1 over epsilon bits. What if I just add some more bits as elements or false positives? So here's what I mean in a little bit more specifics about what I mean. So let's say I have a false positive. In a single hash filter, a false positive is caused by storing the same hash for, false positive is caused by the hash of the query is equal to the hash of some element that I'm storing in my set. We're just going to add bits onto this stored value for the element in my set. So in particular, let's say that my hash function outputs some extra bits, right? Because if I want to add bits, those need to exist. So let's say my hash function just gives me a stream of bits. I'm never going to need more than log n, but let's just say it gives me a stream of bits. So I start with a log n over epsilon bit prefix of this stream. And that's sort of how I hash my function. And that's sort of what I store when I'm storing my filter. Yeah.
Isn't log n over epsilon larger than log n?
When I say like
when you say constant, yeah. It's a function of epsilon.
No, just the constant. So I'm gonna let's say my hash function outputs like 4 log n bits. Okay. That's going to be bigger than log n over epsilon if epsilon is less than like 1 over n cubed, or bigger than 1 over n cubed.
Okay, so we're saying we're going to do this specifically for epsilons that are not too close to 0.
Yes. Usually for filters, if your epsilon is like polynomially small in n, you're never going to have a false positive over any n queries, and it just gets different. You also have problems with like lookups. If I want order one time lookup, you can't really do that while getting that sort of false positive probability. So yeah, we want epsilon to be no less than 1 over poly n. Yeah.
So do you know deterministically you're never going to use more than that many extra bits, or you get really unlucky and happen to need to use a lot of it?
Yeah, we only need this many bits with high poly.
With like,
Yeah, if that ever fails, we'll just throw everything out and rebuild it.
okay.
All right, so I just keep adding bits onto my stored element. That's not going to generate any negatives, because as I add on bits to the hash, if I was actually querying that element, those bits would still match. But if I add only a constant number of bits in expectation to my stored hash, the prefix I have of the hash of x no longer matches the hash of q. Right? Every bit I add causes them to separate with probability 1/2. So after like 2 bits on average, I fix the false positives. So with all of this, we fix the false positive, took me a constant number of bits, and we don't have any new false negatives. And just to emphasize, all I needed for advice was I just needed the item that collided with my query element, which is not super bad. So as I access my database, I just get an actual item back in addition to whether or not the query is in my set. All right, so space. Every false positive I fix requires a constant number of bits in expectation. So if I want n log 1 over epsilon plus order n space, I need to rebuild every theta n false positives. You can just rebuild every n queries. That'll work perfectly fine. You can also de-amortize. In particular, there's a way, and this is part of what we do in the paper, you can de-amortize in place without using any extra space and without affecting any of your other bounds. Right. So you can think about it as every n false positives, we'll just throw everything out and rebuild, or you can actually de-amortize it if you care about worst case systems. Yeah.
We have to worry about the case where there's like many colliding entries, or is that going to be rare?
Yes, excellent. So you only have a constant number of queries that you collide with on average. You can ask your database for all of them, or you can get them one at a time from your database, but that's not going to affect your adaptive performance, because it's okay if I fix this just with, constant probability. Exactly. All right, so this all sounds pretty good. I think the only thing you might be uneasy about is this advice assumption. So we need something from the database. If I get no information, I don't even know if this is a false positive or not. I'm not allowed to fix it because it could be an element actually in my filter. So I definitely need at least to know that this query was not actually in my set. But there's a gap there still. I need to know that the element was not in my set, but I'm asking for an entire new element from the set. Can you close this gap? Right, is Q not in S alone enough information to fix the query? So instead of doing this, we'd really like to do this and only give Q not in S to the filter. So the answer is no. So one of the results in this paper is that if all you get is that Q is not in S, you don't get any other advice. Then you need n log U bits to achieve adaptivity in this case. You need log bits per element. And that's actually tight. You can actually meet that bound. So advice from the database, hopefully I convinced you a little bit that it's cheap because we're accessing the database anyway, but it's more than just cheap. It's actually necessary if you want to achieve adaptivity. Yeah.
Could you hand some information? So you say it works if we hand back the colliding elements. It doesn't work if we hand back only the fact that it collided. Is there a middle where we hand back half an element's worth of stuff?
That's a great yes. So all we need is if the advice is only the next bit to append to the hash, that's enough. So if you care about size of, then you can just get that one bit, and that's enough. If there may be some notions in which that's expensive, and yeah, I don't know anything about that. But extending this hash, the advice can always just be, oh no, you need a little bit more than. Yeah, the advice can always just be, what is the next bit you need to add to this hash? Or what is the next bits you need to add to this hash?
Do you need to add bits to this as well?
Yes, good call, because I guess that's the same thing. Yeah.
So it's just a question of,
yes.
do I need at least one, or am I already done?
Exactly. Do I need to add another bit? And it's going to not be the same bit as No, you do. You need a little bit more than that. Yeah. So let's 1 or 2 bits eventually. I think we haven't completely thought that through.
That many per colliding.
Yeah, I think there's an interesting open problem actually, which is how much do you really need? And in particular, by the way, when I said that this doesn't work, I don't mean like 1 bit per element. I mean, this doesn't work. You need more information in Q, not in S. The lower bound breaks if you get anything more. So there's still a little bit of a gap there that might be interesting. All right, so let's dive into how some of these filters actually work. So I'm going to talk about Cuckoo filters, which is a specific implementation of filters. In other words, like how you actually store these hash values. I'm going to talk about some more recent work about how to make them adaptive and some advantages and disadvantages of that. So these are all based on Cuckoo filters. So Cuckoo filters are one way to create a filter. It's really practical and it's really easy to modify it to be able to create false positives. I don't need to be extending, I don't need to store variable length hashes succinctly or anything like that. So here's how a Cuckoo filter works. So no adaptivity just yet. We're going to actually use 3 hash functions. So first, I'm going to have 2 log2n bit location hashes. This is going to be based on Cuckoo hashing. So just like Cuckoo hashing, indexes into 2 places into a table. That's the job of these 2 location hashes. And I'm also going to store a 1 plus log 1 over epsilon bit fingerprint hash. What we're going to do is index into a table with 2n entries, where each can store 1 plus log 1 over epsilon bits. So the invariant I want to maintain looks a lot like the Cuckoo hashing invariant. For every element that's actually in my set, its fingerprint is stored in one of the 2 locations in the table it hashes to. So every element has 2 table slots corresponding to that element. If the element is in the set, I need one of those 2 slots to store the fingerprint of that item. All right, so how does this actually work? So to store an item in the filter, we need to make sure the fingerprint is stored in one of these 2 locations. It kind of works like Cuckoo hashing. If one of these 2 locations is empty, that's great. We just store this fingerprint. Otherwise, we need to Cuckoo. We pick one of the fingerprints in one of these 2 location hashes, and we move it to its other position. Classic Cuckoo filter analysis, classic Cuckoo hashing analysis says that we don't get any loops or any bad cases like that with high probability. It also shows I need to do a constant number of cuckoos in expectation, which means performance is pretty good. There's some things that I'm sort of sweeping under the rug. In particular, I need a way to store all of these things so that I know the other slot of every element without accessing the original element. There's sort of a trick to do that in Cuckoo, in a Cuckoo filter. All right, so a Cuckoo filter looks like this. So if I insert an item X, this is its fingerprint, 0, 1, 0. If one of its slots is empty, that's great. I'll just store 0, 1, 0 right here. Otherwise, if both of the slots are full of other fingerprints, I'm going to take one of these 2 fingerprints. I'm going to move it to the other location. In this case, this other location is empty. That's great. So I move 1, 1, 1 over here, and I can store 0, 1, 0 in here. So that's the idea of how a Cuckoo filter works. On a query, I need to look for the fingerprint of the query in both locations. That immediately gives me no false negatives by the invariant of the Cuckoo filter. For false positives, there's some y stored in like let's look at one slot of Q. There's some y stored in that slot. The probability that it has the same fingerprint is 2 to the 1 plus log 1 over epsilon, which is epsilon over 2. I'll take the union bound over the 2 slots for the query, and I get probability epsilon of a false positive. So Cuckoo filters right away give me all of the bounds that I want. They're really pretty similar to single hash function filters. So the space isn't great. We have 2 n log, this is actually 1 plus log base 2 of 1 over epsilon plus 2n bits. So we have an extra 2 in front of this n log 1 over epsilon term, which is not ideal. But you can improve that using classic Cuckoo hashing optimization. Like I can split slots into bins, decrease the total number of slots. That actually winds up improving your total occupancy rate. You can get this down to 1 while retaining good performance. All right, how can we adapt with a Cuckoo filter? So there's actually independent work to this other adversarial notion of adaptivity that used a cuckoo filter to fix false positives heuristically. So we're not quite going to get worst case bounds, and I'll talk about why we don't get worst case bounds. So the adaptive cuckoo filter gives a heuristic way to fix false positives, and here's where we're using this idea of changing the hash function. So the idea is we're going to store a little bit of extra metadata. We're going to store an extra S bits per slot. I'll call those hash selector bits. And rather than one fingerprint function, I'll have one fingerprint function per every value I could store using these S bits. So I'm going to have 2 to the S different fingerprint functions. If we have a false positive, we change the fingerprint function of the stored element to the next fingerprint, update its hash selector bits accordingly. So what does it look like? Let's say I have a query Q. I'm going to look it up in the I'm going to look it up in the filter. In this case, the fingerprint of my query is 010. I look it up in the filter. I find the fingerprint. It says yes, but I find out from the database that this is a false positive. Then what I'm going to do is I'm going to change the fingerprint stored in this slot. So I take my element X, which is stored in this slot. I need to get X, just like we did in this other data structure. I need to get X from the database itself. They have the same location slot, but I'm hoping that the other fingerprint of X, this should be a 0 right here. I'm hoping that the other fingerprint of X doesn't match the fingerprint of Q. So if there's a false positive because these 2 fingerprints match, I update this slot to be 0, and I update the stored fingerprint of X to now be the 0th fingerprint of X. So fingers crossed that fixed my false positives. Maybe I have, maybe I haven't. Yeah. So all we do is we go to the next fingerprint function, we update the fingerprint of the stored element, and I want to emphasize this still requires access to our original set. So this is really simple. You can code this up in like 10 minutes if you already have a working cuckoo filter, and it works pretty well in practice. So this is from the original paper. This is on some network trace data, basically just a stream of 5 tuples. We want to know, is this one that we've actually seen earlier in our stream? So the y-axis here is false positive rate. Lower is better. False positive rate here being defined as how many false positives I've actually seen, divided by how many queries I actually see. And then the x-axis is basically size of the set divided by number of queries. You can think of this as how far spaced out queries to the same element are. So as it moves over to the right, it should be getting a little bit more difficult on average, although we can see it actually doesn't get too difficult. The takeaway here, these are different parameter settings for what's F. They had a couple different strategies, etc. Up here, these blue stars, that's a normal cuckoo filter. Down here are the best adaptive cuckoo filters. So we get about a factor of 10 performance improvement just with, so the diamonds are if you have 1 hash selector bit. So just with 1 hash selector bit, I get 1/10 as many false positives on a network trace, which is pretty cool. But this is not adaptive. So the proof for that is if I do 1 over epsilon to the 2 to the s queries, I will have some query that collides with some element on every single one of the fingerprints. So if I do this number of queries that doesn't depend on n, I'm going to have some queries that cannot be fixed using this algorithm, because any hash selector bits, I'm still going to have a collision. So for example, on this slide, I said this works really well with s equals 1. This good performance, even there, on 1 over epsilon squared over the queries, we cannot fix them. We will never fix them, in fact, intrinsically with this algorithm. So even though it does well on sort of these practical data sets, it's very, very far away from being adaptive. This is not the only way to fix false positives with a cuckoo filter. And this may have been a way that sort of you thought of when I first said, let's fix false positives with a cuckoo filter. So if I have a collision, something that might even be easier to do, rather than changing the fingerprint function, we already have a way to resolve collisions with a cuckoo filter. Let's just take the element and move it to its other slot. So here I have a query, fingerprint 110. It matches the element in this slot. Rather than changing that fingerprint, I'm just going to move it around the table using exactly the same cuckooing method that I had before. After I move those elements, Q is no longer a false positive. So yeah, when you have a collision, move the item to its other slot. Just like in normal cuckoo hashing, we do that recursively. What's interesting about this is that it's something called support optimal, which I would argue is kind of the, other than adversarial adaptivity, this is kind of what you want out of an adaptive filter. So we're going to get 1 plus little o of 1 times epsilon false positives per unique query. What does this mean? When we have our sequence of queries, every time there's a new query, it's a false positive with probability epsilon. There's nothing we can do about that because of the lower bound. But if I have repeated accesses to the same query, no matter how they're spaced out, and no matter what's between them, each repeated access to the same query is going to have a little o of epsilon false positives on average. So up to this extra little o of 1 term, this is exactly what we want. If a query is new, false positive probability epsilon. If a query is seen before, I've usually fixed it. Is this adaptive, this sort of moving around? The interesting answer is that it's not. You can do a birthday style attack. So in particular, if I have root n over epsilon squared queries, I can find 2 different queries that collide with the same element in both of its locations. So I can find a query that collides with this element in its first location and collides with its fingerprint, and collides with this element in its second location and collides with its fingerprint. So an adversary, if it's clever about what it does, it can start with root n over epsilon squared queries, keep whittling down queries that don't satisfy this property, and eventually get a pair where by alternating between Q1 and Q2, you're always going to get a false positive. So there's a birthday attack where an adversary can actually get to false positive probability 1.
How does that not violate the second bullet point?
Yes, excellent. So the difference between these is this is per unique query. This is in terms of for any sequence of queries given ahead of time. The number of false positives is epsilon per number of elements in that sequence. Here, the adversary can change the sequence based on the false positives as they come in. So if you have like a practical data set, this is probably good enough. But if you're worried about someone driving your false positive rate really high on purpose, it's actually not going to be enough. So the benefit of moving things around is that you don't need to store any extra bits. And it's also very easy to implement because basically when you get a false positive, you just call this cuckoo things around function, which you probably already have from your insert function. The downside of this, and probably the reason why they didn't do this in the first paper, is that you have a lot of cache misses on adapts. So inserts are really expensive in cuckoo hashing because you have to jump all over your table. And each time you're likely to get a new cache miss. So every time I have a false positive, I'm getting like insert cost, which in terms of like real world wall clock time is generally going to be more expensive than just updating the fingerprint function locally. So it's a little bit easier. It's a little bit easier in some ways, but it might have this downside if you really care about adapting quickly. But it actually gets slightly better performance. So this is basically exactly the same plot, same data, same different filters. The filter that moves items around is on the very bottom here, and it does a little bit better. What's interesting about this, it does just about a factor of 2 better. That factor of 2 is due to this extra hash selector. So if I'm storing 1 bit per slot in order to keep track of what fingerprint I'm using, that makes my fingerprints 1 bit smaller, which increases my static false positive rate by a factor of 2. The takeaway from this is basically by moving things around, you fix things just about as well, and you're not wasting space for this extra metadata, which actually improves your performance by a little bit. One other thing that's fun, I think, from this result. Any filter, this is sort of a sketch of the lemma. Any filter that has, like the idea is order 1 configurations for any element is not adaptive. So if I can only store an element in this place or this place, that's not adaptive. If I only have a constant number of fingerprints that I'm cycling through, that's not adaptive. No strategy like that is going to be. And the proof is basically a general, I mean, I have to define what I mean by configuration, but basically it's a generalization of the birthday attack. I'm always going to be able to find a query that messes me up on every configuration of a given element or a given set of elements. But we saw an adaptive filter, and I want to sort of make it clear what the distinction is. I think this is really important. So the filter that I talked about earlier on, I said every time I fix an element, I'm only going to add on a constant number of bits on average. That's the distinction. Constant number of bits on average is sufficient for adaptivity, but a constant number of bits worst case is not sufficient for adaptivity. In particular, if I have n different queries I'm adapting to on that old hash, for one of them, I'm going to need to add order log n bits just to that one element. So you need to be able to allocate resources unevenly if you want to achieve adaptivity. Part of the reason this is interesting is because if you want to implement this paper in practice, one of the most annoying things is you're storing these variable length hashes. It's one of the biggest obstacles to, sitting down and coding it up in, 20 minutes like you could do for these other filters. You actually need to do that if you want to get worst case adaptivity. That sort of begs the question, can you take this idea of something like hash selector bits, which work great in practice, and allocate a variable number of hash selector bits, thus getting all of these practical benefits and worst case adaptivity? Yes, you can do that. So that's called the telescoping adaptive filter. You used to use a variable number of hash selector bits per element. You want to encode them really succinctly. You can use arithmetic coding, which is kind of neat. One of the nice things about this is you can actually use a fractional number of bits per element. So I talked before about that one element per slot being, the one bit of metadata per slot being a huge problem. If you use arithmetic coding, it's cool because you can use a fractional number of bits per slot on average if you want to, which ekes out a little bit of extra performance and kind of closes the gap between the two filters. It's reasonably competitive with other filters in practice. Arithmetic encoding is expensive, but it's not that expensive compared to something like a hash function. So you get pretty reasonable throughput while still getting worst case adaptivity. That said, when adapting is easy, it's still not worth this extra cost. The best thing to do when you have a set of data that's really easy to adapt to, just shift things around using this cuckooing method. If you have something a little bit closer to being adversarial, you might want to take this extra cost. So adaptivity can help us by improving filter performance. And simple methods can be effective in practice, even if they fall short of worst case adaptivity. So a couple of open problems. One thing is, what can we do without advice? So we can't be adaptive. We can't even really fix a false positive very well. So really the question here is there a notion of limiting the adversary where they're nothing like adaptive, but they still sort of encompass what you would see in some sort of reasonable application? Or we can do something like hiding false positives. You can't really fix a false positive if you don't get advice, but can you do something like hide false positives from an adversary without actually fixing them? Sort of another way of phrasing this is it'd be nice to get a simple practical way to fix positives in the short term without any overhead. So right now we have this sort of, you can store some extra metadata, that's overhead, it's not great. You can move things around, that's also overhead in terms of cache misses. Is there a nice way to sort of shift things around in terms of an adaptive filter without having either of these costs? This isn't necessarily related to adaptive filters, but I think it's an interesting open problem. Right now, there's a gap between the lower bound and the upper bound. So the lower bound I showed was n log 1 over epsilon, but everything I talked about today gets an extra theta n. And in fact, this is the best note. Do you really need that extra theta n term? Or is there a way? So you need this much space if you're doing single function hashes. By getting rid of single function hashes, can you compress a filter even lower than you would be able to otherwise? Thank you very much.
So one class, which seems like it's maybe a type of adaptivity that seems relevant here, is sometimes the connection to your database has some sort of time limits. And so if you hit a false positive, you're more likely to hit that timeout, and therefore it's more likely to be requeried. I guess what I'm saying is, like, is there a natural way to capture that that's less powerful than just like an arbitrary adversary?
So you're saying that there's a certain, is it certain queries or a certain fraction of queries that cause these timeouts? Like is some query always going to cause this
I
timeout?
guess what I mean is just imagine that conditional on being a false positive, you're more likely to see there's some probability of a requery. And if you were a proper negative, it would be less likely to be requery.
I see. And you want to sort of minimize the number of total timeouts.
Or you want to minimize your false positive rate. And this is the one mechanism by which your false positive would be higher than usual if you weren't.
I see. I'd have to think about it. My first impression is probably you just want to have the least false positives possible, but I don't know. Yeah, I would have to think about that in more depth. I like that idea though.
How do you de-randomize your hash function?
Well, certainly you can't. Yeah. So do you mean like how can you do better than like fully uniform random?
Yeah.
Yeah. So it's a really good question. So yeah. So all of our bounds require fully uniform random. And in particular, sort of the back end of that really space efficient result. It needs fully uniform random filters for basically we use like Chernoff bounds. So it's there's sort of an in-between. There's known practical hash function, or there's known, practical in quotes hash functions that don't require too much space, like twisted tabulation hashing that give you Chernoff bounds. Like for every sequence of M slots, basically you get exactly the tail distribution you would from a fully random hash function in terms of number of elements in a given number of consecutive slots. But those actually don't quite work for us because we use Chernoff bounds twice. Because we're going to have like two different levels of data structure. We need Chernoff bounds in terms of how many things don't work up top, and then we're going to need Chernoff bounds again in the bottom. So I think out of the box, these sort of like classic practical versions of hash functions don't give you what you want because you just get those tail bounds once for any M slots. But I bet that you could make them work if you really wanted to.
So even like say, instead of being practical, like say log n wise independent hash functions, would they be
No. I think, actually, I shouldn't say no. I don't know if log n independence, I don't know what that implies in terms of tail bounds. Maybe it gives you something out of the box. Yeah, I guess I don't know enough to be sure. Actually, let me put it this way. If log n independence basically gives you fully uniform random hash functions, then probably, and if it doesn't, then probably not.
Let's thank the speaker again.
Thank you all.